So my talk is titled Interplay between Mass Spectrometry and Computations in Characterization of Biomolecules. Naturally, it's trivial that combination of experiment and theory is a powerful tool in natural sciences studies. So today I'll address the combination of mass spectrometry and computing for molecular biophysics, but I wouldn't stop on the combined results of these two techniques, but address a question of mutual influence, enrichment of the both techniques on their interaction. And I illustrated by three examples one from history, from present, and from future perspectives. The lectures on molecular biophysics are traditionally started from this famous achievement of determination of the structure of DNA molecule by Watson and Crick, which opened the way for physicists for further studies of biomolecules by physical techniques. And since then, many works were done which may be positioned as bricks in the wall of modern castle of biophysics. But with time, early works become obscure by so-called sense of time. So I would like to tell about one of such early works made in our institute, which can be considered as a brick in these studies. So when the double helix of DNA was deciphered, it was established that it is stabilized by complementary pairing by hydrogen bonds between nitrogen bases. And a question for physicists was, what is the energy of such interactions? It's physical thermodynamic parameter of intermolecular interactions. And so scientists from our institute for Low Temperature Physics and Engineering of the Ukrainian Academy of Science, it's located in Kharkov, in far 70s of the last century, decided to address this problem. They were headed by the founder of our institute, academician Verkin, and his co-worker, academician Janssen, and young scientist at that time, now academician as well, Leonid Sukhodub, and they implemented also the advanced at that time, the first soft ionization mass spectrometric technique, field ionization mass spectrometry, which allowed them to obtain mass spectra not only of single nitrogen bases, which was achievement at those times, but associates hydrogen bonded clusters of these nitrogen bases. So they decided to measure the energy of interactions, and they applied what is in fact traditional physical chemistry method of establishing temperature dependencies of formation and decay of complexes of molecules, then construction of Arrhenius plots, and deriving enthalpy of interaction between two compounds. With this purpose, they developed so-called temperature-dependent field ionization mass spectrometry, when reaction medium was created in the gas phase by nitrogen bases. And this was the trick, because earlier only simple volatile molecules were studied, and creation of the gas phase of fragile biological molecules was a real achievement. So by these techniques, they determined the interaction energies of nitrogen, of pairs of nitrogen bases, and this work was published in 1979. It's well cited by now in the corresponding works. Citation is more than 400 by now. And at that time of the 20th century, some empirical quantum chemistry methods were under development. And you remember this name CNDO, MNDO. And what is semi-empirical? Because at that time of development of mathematical processes, not all parameters can be calculated by initio, but some of them were taken from experiments, empirical parameters, data. And also they were needed to check whether the calculations produce the data comparable with experimental results. So the theoreticians used this data obtained in our institute, namely Professor Hobza from Czechoslovakia at that time. I was still a student in these years, but I remember how he visited our supervisors and they discussed their results, and Professor Hobza collected such experimental data to parameterize the techniques which he was developing, and then he published books on intermolecular interactions in English, and it was translated in Russian. So these experimental data of interaction energies of DNA components were used by theoreticians as parameters of some empirical methods of quantum chemical calculations developed at that time. So this is such an early interplay of mass spectrometry and quantum chemical calculations. And later on in the following years, maybe already 3 generations of scientists of our institute are applying mass spectrometry to study interactions of DNA and its components with various agents. Here, I just marked the dates of PhD works and the objects: water, hydration, various drugs, anticancer, antimicrobial, amino acids related to problem of nucleic acid protein recognition, ions, salvation, cryoprotectors. And many calculations in collaboration with these works were performed by Stepan Grigorьevich Stepanyan, who is presently the head of our biophysical department. And you can see among these names the name of our present chairman of our current session. So, but for the second example, I selected more recent results on interaction of biomolecules with cryoprotectors. This work was performed before the war in collaboration with the Institute for Problems of Cryobiology and Cryomedicine, which is also located in Kharkov. And in general, one of the functions of cryoprotectors, there are many functions, but the main is to replace water environment, water molecules, for organic compounds with a low freezing point to keep the objects in liquid state at low temperatures. And in this work, we studied various cryoprotectors, including polymeric cryoprotectors based on oligomers of polyethylene glycol, PEG, depicted here. And the problem was, what are molecular mechanisms of action of cryoprotectors? Whether they just change the properties of the solvent, decrease the temperature of freezing, or they somehow interact with biomolecules. To start with the mass spectrometry results, it should be mentioned that such polymers are polydispersed compounds, which means that they are not characterized by the mass of one compound, but they contain a set of oligomers with different number of monomers. And in mass spectra, they present such bell-shaped dependencies of these oligomers. And then can be recorded in protonated form, and they very actively bound monoatomic metal ions. Here are silver metal ions in this spectrum. And then to our co-workers, postgraduates at that time, Valentina Zabnina and Vitaly Chegovets, they started to apply molecular dynamic simulation to simulate these clusters observed in the mass spectra. It's well known, it's not new result, that polyethers actively bind trap metal ions. They made calculations for some new species, in particular silver ions, and in dependence of the length of the chain, it wraps around these ions in various configurations. And what is important, this structure is preserved in water environment, so polymers really trap the ions from water environment and surround them, keep them in the system. And the reason for stability of such clusters is similar to the case of well-known crown ethers, linear chains of oligomers form crown ether-like structures around metal ions, and they are electrostatically attracted by oxygen atoms, which bear partial negative charge. it's okay, but then in these studies, we have made some small discovery, which is theoretical predictions, which was then found experimental confirmation and experimental observation. What is this about? Valentina Zamnina asked such sacramental question. We are working with cations only, and papers are on cations, but what is the fate of anions? What happens with anions in such system? And she simply replaced metal ion in the input configuration, here the parameters of calculations, by chloride anion. And it appeared that the chain polymeric chain also wrapped around the anion, but in the inverse configuration. Here positive interact with oxygen, and here negative interact with CH2 groups. So there was a theoretical prediction, and then we tried to make mass spectrometric experiment switching the mode of ions registration to negative ion mode, and indeed we observed similar sets of clusters of chlorine anion bound with PEG. And here are also some various confirmations how it may happen. So this was with monoatomic ions. And then, of course, for cryobiology, it was an interesting task whether the oligomers will wrap around biological molecules, around biomolecules. So we continued this work with small biomolecules accessible for mass spectrometry with amino acids and proteins. And here is histidine amino acid, which was used as hydrochloride. And in solution, it dissociates for histidine cation and chlorine anion. And in the positive mass spectra, we observed these sets of histidine bound with PEG oligomers, and in negative ions mode we observed chloride anion bound with PEGs. And it's not the only one peak, it's the distribution which confirms the validity of this data. And then calculations were made, and they showed that positively charged group of histidine is surrounded by such a crown ether-like structure of oligomers with oxygens turned to the positive group of histidine. The next several amino acids were studied. The next was proline. It wasn't hydrochloride, and it can form both protonated and deprotonated ions. And in positive ion mode, we recorded the clusters of proline, protonated proline with oligomers, and calculations show the same picture of oxygen turning to the positively charged group and hydrogens to neutral. And in negative ion mode, there wasn't chlorine, but proline anion, and also clusters less intense, less stable than positive, but clusters, and calculations showed that in this case, proline anion is surrounded by CH2 groups of PEG oligomers. And if we have a Zwitter ion, then positive charge of this Zwitter ion of amino acid is surrounded by oxygen, and negative charge is surrounded by hydrogen. So there's such intricate twist of this oligomer chain. And then the same experiments were performed with a set of nitrogen bases. Here, examples of cytosine and adenine protonated in protonated form are shown. And again, these clusters of all oligomers which wrap around, bind around amino acids, nitrogen bases were recorded, and calculations have shown the similar situation, that polyethers, there are polyethers of three lengths, 4, 8, and 12 oligomers in the chain. They also wrap around biological molecule cytosine in the present case. The longer chains coat this cation completely. So It was shown in this part that PEC protector replaces water molecules in the hydration shell of biomolecules. We are wrapping around the charged group, so it's not just a component of solution, but it protects biomolecules by replacing water molecules in the hydration shell. And there is another branch of investigations connected with pegylation of biomolecules related to drugs preparation, but it's another story and not now, not here. So this was the second question, example related to small molecules. And now the next one, general mass spectrometry. It's not our results, but of the whole community. This is the mass spectrometry of large biopolymers. And to transfer biopolymers to the gas phase was really Nobel Prize worth task. The reasons are, everybody knows from our so-called experiments at the kitchen, chemistry at the kitchen, when we thermally process our food, it don't evaporate, it undergo thermal denaturation. And physical basis is that if the temperature of thermal degradation is lower than the temperature of evaporation, it's impossible to evaporate the molecule. And this is the case of the majority of organic polymers, biopolymers, and large biomolecules. So to overcome this problem, the solution was found. When it was done, it seems that it's very simply, namely to separate large biomolecules in some media. For example, the simplest case, it's solution in the solvent of volatile molecules, or to co-crystallize with small, also volatile organic molecules, and then the heating will cause evaporation or sublimation of small volatile molecules, which will take with them to the gas phase single biomolecules. And this was the basis of electrospray technique and matrix-assisted laser desorption ionization. It's easy to say, but it takes maybe 2 decades of efforts for engineering practical realization of this idea. And then in 2002, the Nobel Prize was awarded for development of self-desorption ionization methods for mass spectrometric analysis of biological macromolecules. I don't place here the names of the Nobel Prize winners because there are only 2, and maybe maybe more than 10 or 20 people were worth of this prize and were mentioned in Nobel Committee press release. But yes, it gave a tool for mass spectrometers, but I would like to stress one thing which is underestimated, underrated by now. This is the significance of this discovery for molecular physics in general. This is that separate macromolecules can exist in the gas phase, because earlier in the textbooks it was written in textbooks on molecular physics that polymers, macromolecules cannot form gas phase, or if they somehow transfer to the gas phase, they will decay there. But it appeared that this is the contribution of our general knowledge in molecular physics. And of course, it opened the way for a new wave of works in mass spectrometry of biomolecules in the gas phase of proteins. The branch of proteomics was developed. And I would like to turn your attention to this book, Nucleic Acids in the Gas Phase. The editor is Valerie Gabelika. I will further give several examples, namely of her works, her team in studies of nucleic acids in the gas phase. And in these studies, there are many, many questions, of course, but I would like to stop on some of them which necessitate combination of mass spectrometry with calculations. And such first question is whether biomacromolecules preserve their native structure in the gas phase or vacuum. And to address this problem, the method of ion mobility mass spectrometry was developed, which can be compared with this famous Galileo experiments when when, in accord to the legend, he threw some objects from the Tower of Pisa, and stones fall faster and feathers float in the air due to the acceleration by air. And this is the principle of this technique. The molecules of exactly the same mass, but of the same but of different structure, will travel in some media. So for this purpose, the tube of mass spectrometer is, the vacuum in the tube is spoiled. A bit of inert gas is introduced to this tube to make a media in which these ions will be deaccelerated. And so compact ion reaches the detector faster, and extended structure moves slower. And here is the picture from one of the first papers on this subject on proteins. So the polymers in this extended structure, they travel slower, and compact ones travel faster. And these experiments necessitates quantum chemical calculations of the structure, the shape of molecules, cross-sections of these structures, and all other data necessary for interpretation of mass spectrometry experiments. And here are some examples. Many works were performed for proteins, and there one of early results, again, of team of Valery Habelika, where when they studied by this technique the movement of dinucleotide DCC. And its structure was manipulated by change of the temperature. So at the lowest temperature, this nucleotide has stacked conformation, stacking of the nitrogen bases. At higher temperatures, there was H bonding and stacking. Weak stacking was destroyed, and at higher temperatures, many different conformations due to movement, thermal movement of this dinucleotide were realized. Such a result with this technique. And here, since we have school here, I can recommend such works, for example, computational strategies and challenges for using native ion mobility mass spectrometry in biophysics and structural biology. And the graphical abstract to this work is exactly what I am talking about: mass spectrometric experiment, calculations, and on basis of calculations, again, new mass spectrometric experiments. So many different interesting experiments can be designed, can be invented to check by these techniques. For example, in electrospray, biomolecules are spotted in the form of aerosol in some solvent, as it was already told. But then in vacuum, the solvent is evaporated, and the conformation of the molecule may be changed. So this was studied in these works. And now I'll return for a moment for our results on nitrogen bases with polyethers. We have made it just before the war and maybe this COVID pandemic, so unfortunately they are terminated, but these were the first results. At first, a droplet, no, it's clear here, but a droplet of methanol was modeled, and its decay in vacuum, how it evaporates. And then our complex of nitrogen base with polyether was positioned in this droplet. And again, there is no time to show a movie, but several subsequent snapshots, and it's shown how methanol molecules, in this case methanol, are desolvated from this complex, and the structure of biomolecules surrounded by polyether is obtained. And there is one more reference for review of this team about what mass spectrometry in combination with calculations can do for nucleic acid research. Here, some structures are shown: groove binding, biologically active agent, stacking agent, protein nucleic acid interactions, and as a result, thermodynamic parameters, including enthalpy of interactions already for such large molecules, shape, structure, stereochemistry, and other parameters of these structures. And here maybe the last results, which I would like to show with connection to other research of our department, which was performed by the head of Department of Molecular Biophysics during the whole 20th century, by the beginning of the 21st century. It's Professor Blagoy Yuri Pavlovich, one of the famous persons in Ukrainian and Kharkov biophysics. And the main direction of his studies was metal complexes of nucleic acids in solutions. And one of the main techniques applied to biophysicists know this film. It was the melting of DNA. Double-stranded DNA with temperature was separated to two separate strands, and the temperature of this transition depends on the structure and whether something is bound to DNA or it's native. So it's possible to estimate the parameters of binding. And why I'm talking about this example, since again, in these teams working with mass spectrometry invented an approach of simulated such curves of melting under mass spectrometric conditions. In the gas phase, these curves are obtained in liquid, and in the gas phase, they changed the energy, the temperature of such complexes of DNA with groove binding agents by increasing energy of collisions of double strand with some buffer gas. Not going into details, but they obtained practically the same dependencies in the gas phase as it was in the liquid. And these are the names of these works: gas phase thermal denaturation of oligonucleotide duplex, and these complexes with minor groove binders.
Marina, 35 minutes.
Yes, yes, I am already practically the last slide. It's outdated information announcement of some mass spectrometry event, but I placed it just to show the subject. It's computational mass spectrometry for proteomics. So this field is actively under development, and I showed the possibilities of application of computational techniques in this field, and it's possible to continue such experiments, and I would like to turn attention of people engaged in computations, namely to these problems. So conclusions of three examples: history, that thermodynamic data obtained by mass spectrometry helped to parameterize semi-empirical calculation methods at the early days of development of both approaches. Computer calculations help not only to model objects observed by mass spectrometry, but to predict the existence of new objects, this observation of complexes with anions. And there is a vast field for the application of computational techniques for the interpretation of mass spectrometry data on biomacromolecules, gas phase structure, gas phase properties, thermodynamics, sequencing, and interaction with various agents. And happy computation to you, and thank you for your attention.
Thank you.
I finish.
Yes, thank you very much again. And some questions, Sergey first.
Thank you very much, Marina Vladimirovna, for such nice lecture, very clear and very interesting. I would like to ask you about complexes that you show of argentum ions with PEG, as well as sodium ions with PEG, and also chlorine ions. So you showed that you predicted some complexes of chlorine with PEG. And this is,
yes.
Very interesting because chlorine is structure breaking ion. And this complex is possible because water molecules are not so constrained by the ion. And this exchange is possible. And in the case of argentum as well. And there is a rule that if you have two ions like argentum and chlorine, they could form some complex, cation-anion complex. And if you can have such sweet ionic complex, you probably can detect some argentum chloride with PET. It should be bigger in your by mesh in your mass spectroscopy complex. So if you look at this spectrum, or maybe you can find some cation-anion complex with PET.
Yes, thank you very much for your question. And by now we have observed only clusters with cations and anions. And if cation and anion will be combined, they will be neutral, and maybe they are formed in our media, but our method cannot detect neutral structures. So we cannot see such a complex if it's formed. I didn't show the calculations of sodium chlorine, but the neutral structure, which has some distribution.
And
Yes, we cannot observe it. We cannot observe neutral structures in our experiments. So this is a problem. We can observe only positively or negatively charged part of our system.
Yes.
And also it dissociation depends on the surrounding, if it's polar solvent. Yes, Marina, if it's for electrospray ionization, we use normally methanol or some other polar solvents. There is this.
Yes, but here electrostatic interactions are much more strong than interactions, hydrogen bond interactions of solvent and solvent with polyethylene glycol. So this is just a moment. This structure that in water environment and in methanol environment, these complexes survive, namely as complexes, not as separate ions and polymers. But it's an interesting field to continue, and unfortunately, this crazy war stopped some of interesting investigations, but we hope to continue them when it will be possible, and maybe in collaboration with some people who become interested in these problems.
Thank you. Some other questions? Maybe audience of Zoom, online audience? If no, Marina, thank you very much. It was really good final lectures because it's showing the connection between experiments and calculations.